Hi guys, we are into session of transducers. I always have been wondering about transducers and how does it manage so many faculties at a time. For example, body, we see so many things at a time, we smell so many things at a time, and we hear so many things at a time. But transducers distinctly differentiates varieties of things that we see at a time, or that we smell at a time, or that we hear at a time. Now this has been intriguing for me, and I have been always thinking, what does this transducer do to differentiate things? And I got certain ideas. I've framed certain ideas which I'm presenting over here. Now just check it out, how it goes with you all. Sound is longitudinal wave. It's also mechanical wave. It's mechanical wave because while traveling, it moves via rarefaction, compression, rarefaction, compression, as a result of which it creates disturbance in medium. Now this sound, this rarefaction and compression passes through meters. This is our ear, passes through meters and creates disturbance at eardrum, or rather it keeps this eardrum vibrating. This vibration is then transferred to malleus incus stipes, and stipes knocks at the oval window. That oval window then passes it on to cochlea. Now there are semicircular canals and all those things, but I'm not covering up those because they are concerned with balance of body, so I'm not concerned with that. So we move into cochlea. Now in cochlea, what I'm concerned with is this portion. Now these are cochlear nerve, and there is temporal membrane here, which I would be showing later on. Temporal membrane, and these are hairs of mechanosensory hair cells. The temporal membrane which compresses against the hair. Now this compression again depends upon the vibration that has been brought in from hair to hair. Alright, more the vibration, more the disturbance. How it is concerned with transducers converting that mechanical energy into electrical energy. Alright, so this is the basic part that we have got to know. In terms of diagram, then I would be concerned with this portion, because more the disturbance, more the pressing of this tectoral membrane, owing to which there is more displacement of tectoral membrane, which we would see how it is concerned with transducers converting that mechanical energy into electrical energy. These two tables just shows significance of cochlear region with frequencies, like low frequencies, these are the low frequencies, medium frequencies, these are the medium frequencies, high frequency, these are the high frequencies. All right, and this is how it is distributed, right? So at this part we have 200 hertz, and then here we have 400 hertz sensitivity, and so on and so forth. This is the tectoral membrane, these are the hairs, and these are the mechanosensory hair cells, and this is the cochlear nerve. Alright, so basically tectoral membrane to press against hairs of cells depending upon disturbances created by sound waves in cochlea. So this is the rough picture. Okay, so this is the mechanosensory cell, this is the hair, this is tectoral membrane, and this is cochlear nerve, which is going to carry the impulse which transducer converts from that mechanical energy to electrical energy. So this is the membrane, tectoral membrane. Now see, this is the force which is being applied. Alright, so endolymph responses to vibrations of sound waves, alright, and generates force over here and pushes it down. Alright, so deflection of these mechanosensory hairs of hair cells generates electrical signals, and who helps in doing that? It's the transducer. So this is basically what is happening, where D is displacement, work is equal to force into displacement, which is equal to energy. Transducer converts these mechanical energies to electrical energies. All right. Energies of sound varies with amplitude and inversely with wavelength or directly with frequency. Now this part of video talks about difference in wavelength. Now when we check out over here, we'll find we are assuming that the amplitude is the same. All right. So here the wavelength is high, wavelength is low, and wavelength is the lowest. And energy is inversely proportional to wavelength. So in terms of wavelength, what we would say is that the energy in this wave is much more than this, That's what I have represented here. And why is it so? Lambda 1 is greater than lambda 2, greater than lambda 3, owing to which inverse follows with energy. All right, so this part is all about wavelength. Now let us come, how does it behave here? Now in this case, what happens is, this is obviously tectoral membrane. These are hairs of mechanosensory hair cells. These are mechanosensory hair cells, and these are hairs of those mechanosensory hair cells. All right. Now these are the cochlear nerve, and here we have the transducers, which would be converting this mechanical energy into electrical energy. Now how it happens, let's see. Now this is the first case. Now here, this wave, owing to this wave, there has been disturbances in endolymph of cochlea. So owing to which, what happens is, in pencil is the original position of tectoral membrane. All right, so this has moved slightly below here. All right, so it has pressed the hair cells. All right, so as a result of that, it has covered up distance d1 from here to here. When this wave comes, it has moved still further down. So this has again covered distance d2. Now when I come over here, now this wavelength is very small, so more energy. So as a result of that, ripples have moved the tectoral membrane from here to here. So it has covered up distance d3. So here it was d1, which was smaller than d2, which was smaller than d3, or rather d3 greater than d2 greater than d1. So where obviously, as I mentioned over here, d is the displacement of tectoral membrane. So obviously force into displacement is the work. So force is applied by what? Force is applied by the endolymph, and endolymph applies force. Why? It's all because of these behavior. All right, so that force which is being applied, that is generating this displacement, and this displacement is doing some work. Force into displacement is work. That work is being converted to electrical impulse by transducers. All right, so this is the basic understanding. Let's see what amplitude does to sound, and also let's see what sound then does to tectoral membrane. And the behavior of tectoral membrane is how understood by transducers and then coded in electron volts. Now let's understand the relationship of wave with amplitude and intensity and loudness. All right. So to begin with, we know that human audible range in terms of decibels or loudness is 0 to 120 decibels, which we mention as small d and capital B. All right. Loudness is directly proportional to intensity. Intensity is directly proportional to amplitude square. Formula linking loudness in decibels with intensity I and amplitude A is L dB is equal to 10 log to the base 10 I over I0. L is loudness, dB is decibel, which is also equal to 10 log to the base 10 amplitude square upon A0 square. Now I0 is least audible intensity of sound for human, A0 being corresponding amplitude. Relationship between this and this is square. So if this is I, this has to be A square. चांद छुपा बादल में शर्मा के मेरी जाना सी। चांद छुपा बादल में शर्मा के मेरी जाना। चांद छुपा बादल में शर्मा के मेरी जाना। Let's see what wavelength has got to do with sound, and subsequently how sound reacts on tectoral membrane, and the activity of tectoral membrane is understood by transducers how, and how does transducer differentiate the activities. Alright, let's try and understand.
चांद छुपा बादल में शर्मा के मेरी जाना। चांद छुपा बादल में शर्मा के मेरी जाना। चांद छुपा बादल में शर्मा के मेरी जाना।
चांद छुपा बादल में शर्मा के मेरी जाना। Obviously, one thing is understood, that transducers differentiates all the signals by coding it in different electron volts. Alright, hope you enjoyed this session. Very soon I would be back with transducers and spell. Alright, let's see how my idea goes about transducers and smell. Alright, see you then.